Okay, welcome to week 4 of our MAPS 340, or not 342, MAPS 362. And I want to let you know just in advance, this is a much shorter lecture than last week. And the reason for that is, first of all, the information here is pretty complex, and it's very highly technical. So just leaving it to like fester is really important. And then going back and like listening to this again and then letting it fester. So you're probably gonna have to watch this video like 3 or 4 times to really get what's going on, because it is a very highly technical, really like almost a computer science based idea behind point clouds. So with saying that, so the lecture itself is going to be short, but you're going to need to listen to this several times to really kind of get it. And please make sure you're doing the readings in the textbook, because this chapter in particular, like I'm saying, is technical. So go through the textbook, try to identify what do you understand, what don't you understand, and then move from there. I also want you guys really spending some time with looking at how it is applied in ArcGIS as well. How are the point clouds visualized? How are they structured? How can you manipulate that within the actual software itself? So all of that really comes down to your need to how you handle that, those point clouds. So in saying that, what we're going to cover today is we're going to talk about how we convert point clouds to images. We're going to talk about point-based rendering. So what does rendering actually mean? How the data is actually structured, and then segmenting the point cloud itself. This is all following through with like what is in the chapters of the textbook. So these are just big sections of it. A lot of what we're going to be working with in this class is we're converting the point clouds to rasters. The reason we're doing that is because rasters do allow for more flexibility in analysis of data, and we can actually include a lot more than merely just keeping it as like a vector-based drawing is really what would come out of a point cloud. So we're going to actually convert our point clouds to rasters. So there are different kinds of point cloud images that we can come up with. We can have a height image, we can have a shaded image, we can do point quality images, so looking at intensity and point density. And we can also do quality control visuals. So I'm going to talk about kind of all of these throughout the throughout this lecture today. So that's just but this is just introducing the start of it. So height image creation. There are 3 major steps that we go through to be able to create an image. So the first one is we define the image grid. So what do our pixels look like? How much space are our pixels going to take up? How many points are going to be within that pixel? And then what does our spatial resolution look like, right? So this is that major starting point. So we actually have control over that, because you can't just take every individual point and put it into its own pixel, because everything is an irregular grid. The points are taken kind of all over, and so nothing is actually like in a perfect grid. Even with like flash LiDAR, even the points coming back are still not in a perfect grid. So we need to define our pixel sizes. And really, if you were to try to create an image with every single point on your point cloud, you're going to end up with like issues with like whether it be the like data storage, because it requires so much memory, because you have such tiny pixels. Sometimes you can overkill the number of pixels because your beam width is actually much larger than your resolution. So it's an important concept to kind of remember, that as we're going through, it's not 1 point per pixel. It is a number of pixels over an area with an area. So your conversion here for your pixel size is the area of that pixel, or of the entire scene, divided by the number of pixels, and that's going to tell you your pixel size. So that you should know the area of your entire scene, because you define that before you even collect your data points. And then how many pixels do you actually want? So there is a possibility to define this differently, but this is the simplest version of it. So the next step that we have is going into the determination of pixel heights. So how can we tell what that value is within that pixel? This is this is the trickiest part, really, because when you are when you are taking these pixels in here, or these points, and you create these pixels, we need to come up with what number are we using. So we do something called binning. And binning, what it does is it is the fastest way to take a point. So we have different ways of identifying the binning. For one of them, they take the average, and some of them, they take the one nearest in the middle. So we have our little box, and we have all the points inside of it, and we can say, okay, we're going to take the average, or we can say we can take the one closest to the middle, or we can say we're going to take the maximum, or we can say we can take the minimum. We can take all kinds. So there is lots of different ways to bin, and we will bin based on different reasons, right? So sometimes I want to have that first return. So I want to see what are the highest values, and that's going to give me the top of something. Sometimes I want to know where the ground is. So you know what? My binning is going to completely get rid of all of everything above it, and I'm going to take that last return, and so I'm going to take my minimum height. Sometimes I want the average because I'm looking at an entire area that the slope changes, right? And so I want to take that average as I work through my pixels. So it all comes down to what is your application and why you would do it that way. But one of the biggest challenges that we have with LiDAR is because nothing is evenly distributed, we do end up with like gaps in our data. We have no points in a certain area. So what do we do? So there's a couple ways that you can handle that, and you can actually identify this in your software. So you can say that the height is like undefined, right? You can say just put NA, it's not applicable because there are no points there, and you can just leave it as a shadow. And then that means that anything that you do for computations, you have to exclude those pixels because otherwise it won't work. The other way is doing interpolation. So there are different ways of doing interpolation. We talked about that in our modeling class. So you can choose what kind of interpolation you want to use, and then it will take the pixels around it, or a couple pixels, or the nearest point that's within that pixel, and it'll assign it. So again, there are many different ways of handling it. If you don't want to model those gaps, then don't model them, because it will reduce the accuracy because you are now introducing modeling errors rather than just leaving them as is. In our class, we are going to interpolate because we are creating models. So I need you to fill in those points. So tins are basically an interpolation of pixel centers. So if you create a tin from a raster, you are looking at the center of the pixel, and then you create 4 triangles around it. And so if you do create a tin from a raster, that will help clean up these unidentified locations. But again, it's creating that model. It's a type of that interpolation. Other methods include using a photographic image. So photogrammetry is used a lot now in conjunction with LiDAR. They kind of come together as a package. So those photographs will fill in that empty space and still make it look like it's a full model rather than leaving it as a blank black hole. So we use binning to identify the pixel heights, and then we either interpolate or leave blank all of the no points in the pixel locations. And then finally, from there, we actually convert to a gray value or a color. So everyone remembers gray values or digital numbers from before. So we have 0 is our minimum height, 255 is the maximum height, just like what we did with remote sensing. And then we set a white point to increase the contrast, or we apply a contrast stretch, or you can do whatever you need to try to enhance what you need out of that image. Because sometimes if you have a big elevation difference or big height changes, then it's going to be overwhelmed by that, and it's going to create a bias. So that's how we convert or create height images. Sometimes we'll take it one step further and create shaded images. And this is hillshade, right? So if we don't apply hillshade, then we may not we may not see things that we need to. Like for example, this image that I have here of a landslide, they couldn't see how the slide had actually occurred and where it was and how much it had moved. They couldn't see it. So when they applied hillshade, they were able to project like some of these shadows so they could actually see where that land had slid in that area. There is a way to do this using filters. Going back to filters, so using a gradient filter, we can fill it in. And then we're identifying diagonals, and so we're looking at chessboard type of filtering in this case. So again, we're not going to do like any filtering by hand in this class, but that is something that we will apply the gradient filters to apply a shade to our models or our images. So there are other kinds of images. So two of them that I mentioned was an intensity image and a point density image. So intensity images talk about reflectance strength. A lot of times you'll see anything closer to the scanner is going to have a higher intensity. Anything further away is going to have a lower intensity. In airborne, the same can happen. Although if you are dealing with multiple returns, you're going to see that that intensity is actually reduced when you have multiple returns rather than just a single return. So again, looking here, this is from terrestrial, but we can see that the power lines have a lower reflectance strength versus, for example, the poles, the metal poles holding the street lights, that has a much higher reflectance strength. Then here's a point density image. So these are important to identify gaps in your data or areas that there could be a potential rendering issue because it's overpopulated with points. So this allows us to see how it's being distributed and if we need to make any changes to it, because if we do have point densities that are really high, like for example in these squares here, then we may have to say, okay, well, we need to decimate the cloud just in those areas so that it's all managed to be the exact same point density throughout, because it all comes down to rendering. So when we bring in the data points, the computer can only show so many points. And so we reduce down the point density so that we're not showing everything all at once. So a quality control visual also gives us a quick overview of what we are looking for quality. So flight path overviews. So Pix4D shows something like this. You guys would get that there. And so you can see where the flight path has kind of followed. You can see even in 3D where it's gone up and down to try to maintain the altitude of the airplane. And this is really helpful because if we didn't actually go lower in these areas, we may actually not notice that there is going to be a change in how the LiDAR acquires the data if it stayed straight across and didn't actually dip down into that valley or the coulee in this case. So that is important. It also gives us an idea of where the data is going to be located and the coverage of the LiDAR. It also tells us areas where there's going to be extra overlap along the edges and where there might be gaps along the edges. So you can see the yellow might be some gaps because it's turning around. So this gives us a really good overview as to what the quality will look like in the centers and around the edge of it. We also have overlapping visuals, so overlapping strip visuals. This just shows us where the flights are overlapping, so we know that as it's passing over, these are the areas with higher point density. And then it also tells us the percentage, right? So we can see, okay, this amount is overlapping, so we can trust that as we bring these together and register these images together, that it's going to be the same points, right? And then we're not going to have like some weird angular distortion or rotation of one of them. And so it does allow us to adjust things. And for registration purposes, this is really important. So I already brought up rendering. I'm going to bring it up again here and just talk about it a little bit more detail with this particular slide. There's this little video I want you to go to and check out. It goes over rendering and like, I believe it's silent, but it does show a really good example of rendering. So rendering is, they use rendering to determine the normal direction of a point. So again, going back to that normal direction, which is the perpendicular direction from the tangent to a surface. And this is how we identify how it's going to be rendered. So rendering is how many points we're showing at once, and then how does the computer choose which point to render and which one to show. And that normal direction is what is important to it. So as the normal direction is changing rapidly, it's definitely going to keep those. So it weights them a little bit higher. And then the ones that are flat is not going to weight as much. So you can really see that with, like, for example, this chair here. So as the edges, like the normal direction is changing around those edges, it really identifies those edges and renders those. Where the flat side, it doesn't show that edge at all. It doesn't identify that as something that's important. And then there is, we use nonlinear least squares to try to solve using eigenvector computations. I know, remote sensing, we just keep coming back to those eigenvectors. They're going to haunt you forever. Again, I'm not asking you to do this by hand. So, but the eigenvector computations tells us the weighting of this normal direction. And then therefore it will weight those points and render them, so allow them to appear on the screen with that kind of importance. We can end up with overemphasizing points if it's rendered incorrectly. So you can see here that if we don't have rendering that's correct, we're going to end up with points that are like really overdone. So for example here, well, I'm looking at these chairs. So if we have really low points, we start losing out on the back of this chair. And even here, like, we're kind of losing out on what's happening. You can see that there is a line here, but it's not even showing up in this case. And over here, the points themselves, like, we've lost that handle. And right here, it's at the back. So I don't even know how it got, like, that almost looks like it's seeing through the chair, and it shouldn't see through the chair. so we're ending up with some weird emphasis that's happening, and as we reduce down the points too much, as we keep more, we can see that it gives us a much better view of what these chairs look like. But but as you have that many extra points that are being rendered and shown on your screen, then you end up with then you're going to end up with the case of, like, the computer being slower. So it really slows it down. So if we reduce down the rendering points, it's really all that's being viewed. It's not what's being calculated. So that's another issue. And another thing to kind of separate. Rendering is all about what is being shown on your screen versus what is actually being calculated. So if you're giving it to your client, be aware of this rendering condition and be able to give it to them and tell them this is how many points it's going to render. And this is how you change it. All right, data structures. So here is another kind of advanced topic when it comes to computers. So data structures are the way that the computer ties together the actual points themselves. So one of them, for example, when we're creating a model, now this is, what's the best way of describing this? So when we're dealing with data structures, this is how the computer itself connects the points. How does it show up in pixels? How is it going to relate those pixels to each other as we zoom in and zoom out and rotate in 3 dimensions? So this is really like how the computer keeps those points together, and it's not just based on X, Y, and Z values, right? So because we're having rendering, we have rendering situations. So as we zoom in, it can show more points locally in that location. So if we don't have a data structure which still connects those points that are not showing, when we zoom in now, the computer can start showing it. So this is really like a computer science type of viewpoint on LiDAR point cloud. So this is like really how the point cloud works once it's in the computer. So Delaunay triangulation, we have TIMs. They have to be dynamic or static. And static TIMs is kind of, they kind of bounce between the two depending on the software. But as I zoom in, I start adding points to my point cloud, and I need to start tying them together with this Delaunay triangulation. So How is it representing it? And this is really like point to point to point. It cannot be really done well with rasterized point clouds, but it allows us to work with CAD. So if you're working with CAD, there you go. That's what's happening. As we move into something that is rasterized, we get into things such as octrees and KD trees. So octrees are large data sets that have like spatial indexing and compression. So we take like all these like LiDAR data sets that have millions and millions, hundreds of millions, billions of points, and we'll put them into a software that can handle it. It's indexes everything based on its location, and it compresses them based on that like point density. So there are 3 different kinds of octrees, and I'll get to those a bit, but that's really the idea, is that it says, okay, I'm going to group these together and say, okay, I'm going to compress them into one spot, and then keep like a small database on the side saying that there are these extra points within that one spot. The KD trees is really 3D data. It's called a binary search tree, or it can be a KD tree as well. So you can see here that we have our points that are randomly distributed. It connects it all into a grid. So we have like a 3D grid that it creates. And it finds the nearest neighbor. So that would be the center point, and then it finds the next closest one, and it creates a little box around that closest one. And then it creates the next nearest neighbor, separates up the data again into more boxes. So it starts adding more and more boxes. And then it'll increase the size of the box or decrease the size of the box depending on where these points are located. So we're separating it up based on these cubes, keeping the points closest together in little boxes and points further apart in larger boxes. And I know that sounds like, oh, well, now we're trying to keep a structure of a volume, but instead of having to maintain, what do we have, 8 points, now we only have to maintain 1 equation. So it actually reduces down the data and compresses it. And it's like a priority, right? Like, so it prioritizes, it weights everything, and then we create these little boxes and big boxes. What's really cool about this is as you zoom in and out, the little boxes will appear, and as you zoom out, so you zoom in, the little boxes appear. As you zoom out, the big boxes take over. So that allows for rendering to be a little bit easier in the computer screen. So I wanted to talk a little bit about the octrees because these are the most common ones that you're going to see. So Cyclone uses the KD trees, but ArcGIS uses octrees. So there's 3 major types. So we have the regular region quad tree, we have the adaptive point quad tree, and the 2D tree. So the regular region tree is literally a grid. It just has everything is the same size of grid. It bins everything into one, and you're good to go. You can end up with empty cells. That happens with octrees, and it's really just like that binning component. It's not really a pixel at that point, but it bins them and says, okay, everything in. As I zoom in and out, it just, as I zoom into 1 pixel, then I'll start showing the points. But otherwise, each individual pixel maintains the same number of points that are going to be showing. So it regularly distributes it and keeps the data together, but you end up with these empty cells. You end up with like pixels with a huge amount of data, but nothing else in there. Then we have the adaptive point quad tree. So this one is an irregular grid. So you have some higher density areas and some lower density areas. Every cell has at least 1 point, but it has many. Some of them might have many points. But it does reduce large clusters within a single pixel because we can reduce down the size of that grid for those particular points. So we might say that, for example, we want 4 million points or 4 million points to show up on our screen, and we have 50 million points. So this will look at it and break down the data into like, okay, well, there's a large distribution of points in this area, and they're very wide, and so the point density is really low. So we're going to keep those areas are just going to stay, but we might put 1 pixel in, or 1 point into each like bin, and just leave it at that. The areas of the higher density, we're going to separate those up into much smaller bins, and we're going to keep them all together. And then if you were to zoom in, then we're going to start showing more and more of those bins as you move into it. And then it just maintains all of those data points and keeps, so as you zoom in and out, it's going to adjust those points based on this adaptive point tree. Higher density areas have more points, and that's just what's going to end up happening. And you're going to see that. The 2D tree, this one is also very similar. It is a very irregular grid, but it does have very, they can have very large cells, but there's no empty cells. So you can, here you put in a condition, you say, I want 50 points per pixel, or per bin. I want to call it a pixel, it's not a pixel, per bin. I want 50 points per bin, and so every single bin is going to have the same number of points. And so if you have 50 points that are spread out over 100 meters because of the slope of that area, then you're going to have a very large cell that covers that entire slope, where in other areas you may have a large number, or like a large number of really small cells. This one actually does adapt better than the adaptive point quad tree. This one, it allows for less of an issue with the rendering because I do have a set number of points within each pixel. This one's very computationally expensive. This one's not as much because it knows how many points are in within each. So it does remove any like bias. This one will end up with rendering bias. This one not as much. So they're kind of like trade-off between the two. So I do have an example of them here. So the regular region quad tree, you can see that it's just all, like basically separated up into a regular grid. And I'm using pixels in these cases just to kind of show what happens. Adaptive point quad tree, so you can see how so we have like high density pixels, like more information happening over there. So you can see how in certain areas as like things change, that we show more pixels and there's a higher rendering in those areas, or that like higher density of information in those areas. Then the 2D tree separates up everything into an equal number of points, so you can see how the grid changes in size and shape. Now, if we said that we wanted to have 4 points per pixel, then we're looking at it separated up like this. 2, you can still see that we have a really large pixel here versus, for example, this one or even this one. So you can end up with larger pixels. It happens. But in those, sorry, I keep calling them pixels, bins. they're not pixels, they're bins. These are pixels, these are bins. So this bin is much larger, so you have a lot more information, or not more information, but you have a larger space that it's going to show. So you're not going to have many points show up ever in that particular area. You'll have like one value until you really zoom in and it'll show the 2. Where this one, it's going to start showing those values rather quickly because it is such a smaller space. So that was like really the most complex part. So knowing what each of these are and knowing how they adapt. So these two are very similar. The only difference is this one is trying to get down to a certain, like the threshold of this is a certain area. The threshold of this one is the number of points in the pixel. So they are very similar in 2 ways. So that's just something to keep in mind. They're similar, just one's number of points, the other one is number of pixels, or it comes down to the density of those pixels in that area. Now I'm calling it pixels again, bins. This is a problem about teaching remote sensing right before teaching this one. All right, so point cloud segmentation. So moving into how do we separate out our data points within our point cloud. We're not necessarily trying to identify features in this case. What we're trying to do is identify how each point in the point cloud is different. So a lot of this is automated now. We don't have to think too hard about it. And every type of software, it kind of does its own thing and it's used differently, and everybody segments the clouds as they want. You can take slices, you can take classifications, you can take, there's all kinds of things. So And we segment the cloud a lot because generally you always end up with more information than you need. And so you're going to find in our project that we're going to actually segment out trees, and we're going to try to identify trees versus a building. And so, and we just do it as a raster analysis rather than going through and like identifying individual points with certain thresholds. So that's where rasters are significantly more powerful than looking at individual points. But if you're working with a CAD software, then you've got to work through this. So we have 4 different kinds of point cloud segmentation. So we've got the 3D hue transform. We have the random sample consensus algorithm, RANSAC. And we have surface growing, and we have scanline segmentation. So the 3D hue transform, it is really, really helpful for determining lines, planes, and cylinders in a 3D space. Cyclone uses it, same with the RANSAC as well. It uses that as well as in another way. ArcGIS, well, CAD, I'm not sure, because there is CloudWorks that you can use from Leica, and I think that it uses 3D hue transform for it, but I could be wrong, so don't quote me on that. So these ones, you can say draw a line, like identify a line in this area, and you can like choose points, and which RANSAC does the choosing of the points. So these are similar, just a little bit different. So here, this is like an automated thing. You can actually register based on cylinders in Cyclone. So this is where it's using that. It's not even, you're not even manually choosing anything. It'll just say, hey, I know that these cylinders look the same. I can auto register based on the plane. And these flat areas, you'll see like a room, and it'll auto register based on the room. And that's terrestrial laser scanning that I'm talking about there, but the same is similar for LiDAR in airborne. So RANSAC, you actually use number of samples so that it doesn't automatically identify something strange. So the random samples, like I said, I could choose a couple points along a line, and then it'll just draw the line for me. Same with the plane, I can choose a couple points on the plane, and it'll draw the plane for me. Same with cylinders. So RANSAC is a little bit more controlled, but it allows for the removal of those outliers so that we're not ending up with like some weird shapes that we don't intend on having. Surface growing is really helpful if you are trying to model things like planes, even cylinders as well. You can say extend to the end of this, and then it'll continue to extend until it has taken up all of those points. And then it'll say, okay, now I've created a plane, or okay, now I've created the cylinder. And you can keep surface growing. Usually you'll just say surface grow, and then you just kind of keep pressing the button until it actually grows into the full thing. So you have to keep an eye on it. Otherwise, it's a computer. So quality control is really important when you're doing surface growing. And finally, we have scanline segmentation. So this is like, look at each individual scan line from airborne LiDAR and process it separately. So if you have straight lines and planes that you are looking at based on the airborne system, then you can identify those straight lines really, really well using a scanline segmentation. It does require a lot more work because you have to look at every single scan line to be able to process it, but it might have that information within that certain line or plane that you are looking for to do that measurement, and you would use that and keep that as your ideal segmentation. So like I said, this is a shorter video than the other one for this week. I would normally have you guys doing all kinds of activities in class, but I guess we are doing it this way. So please watch this like 3 or 4 times. You're going to need it. There's quite a bit of technical information. Please read the textbook because it's going to have more information. Please post your questions if you have questions. So covered a lot today. A lot of technical information, especially when it comes to data structures. So, and then talking about difference between raster and vector all the way through. We are using vector in this class, or not vector, we're using rasters in this class, but it is important to know the difference between them because in most construction projects, you will end up with working with the vector, which you've already done in CAD. So that is everything. So here are my references for today for all of the images that I borrowed from people and to give them credit. and I will see you guys next week.